I'm the presenter right now, right? Yeah. I think, yeah, it should be. People in Zoom, can you hear me?
Yes.
Okay, thank you. Thank you so much.
All right.
Is the right mic connected?
It still says connect.
Yeah.
Oh,
Okay.
okay, cool.
Great. So now we're
Now we're
done.
ready.
Yeah, okay. So it's my great pleasure to introduce Steffi Knoll, as a professor at the Technical University of Berlin, and visiting us here to talk about scalable robustness and distributed control of multi-agent systems. A lot of keywords hitting stuff that we're interested in here as well. So very excited about that. Before Steffi went to Germany, she was in Uppsala, the Swedish connection. And for that, she did her PhD in Ireland and in Newcastle in Australia. Yeah, I don't know if there's anything else I should add. I think she has a lot of interest that intersect, as I said, with his department. So there are some more meeting slots for this afternoon, but also, of course, lots of time to ask questions, I hope, after this talk. So
All
please.
Thank you so much. I first of all want to thank Emma, Venkat, and the department to invite me to talk about my research, something that is very difficult every now and then to find time for research. So it's great to be here for a whole day and talk about nothing else than that. And also thank you so much for organizational stuff, making it very easy for me to come here. Much appreciated. Yeah, research. Wonderful part of being a professor is to be able to do research. Maybe not as much as we sometimes want, but anyway, here we are. And I'm very excited to talk to you about scalable robustness and distributed control of multi-agent systems, something that in one way or another I've been working on since my PhD in slightly different forms and had evolved over time. And I thought it's maybe a nice opportunity to summarize some of the things we've been doing. And I also already this morning realized that this is very close to what a lot of you are doing, and I'm looking forward to the talks in the afternoon to find out even more about it. And there's the key to advance the site. Perfect. I thought I'd give you a small introduction, even though I guess 95% of you don't need this because you work on this. But anyway, a small intro with a bit of literature review to see what other people are doing and connect to that. Very short. And before I want to talk, and after that, I want to talk about 4 different approaches or 4 different things we've been working on or are working on right at the moment. One is a scalable notion of input to state stability. Then looking into how can we make structural changes in a network scalable, in the sense that can we allow a network to change its size or the number of agents or the connections in between them and still maintain some desired properties. That connects to maybe having to readjust some controllers on the go as the as a network structure changes. So that brings us to online distributed design. And quite recently, we are looking into more general forms of agents, and in this case, MIMO agents. And this is something at the very end to wrap up. So let's start with an introduction. I do not tell you anything new, I guess, if I tell you that the world around us is getting more and more connected. And you see here 3 pictures of examples that I don't think I need to explain. And as we know, we are doing these connections of smaller systems because we see a lot of advantages in it. One advantage is that if we connect small systems into a large system, then the overall system can achieve goals and do tasks that the small systems couldn't be doing. And very often there's more robust in the sense that if one small component fails, the rest of the system can operate still, hopefully as if nothing happened. So if one car breaks down, that shouldn't ruin the entire traffic network, of course. But if you have connections between agents, whether they are physical or by information exchange, when you do have a perturbation or a distortion in the network, this will then affect other agents through those connections. And if we haven't set up in our network in the best possible way or in a way that allows that, it could happen that small perturbations amplify as they travel along the path or the walks in the network. And this can then lead to cascading failures or even render the entire system unstable. And of course, needless to say, this is not what we want because it worsens the overall performance of the system. So what we want to do, or the overall arch of my work in this area, has been to provide a scalable notion of network performance, prohibiting exactly that behavior. So first of all, formalize that in a decent way mathematically, and then make sure this effect does not happen. For example, by appropriate controller design. And we want to maintain this property despite structural changes in the network. So as I said earlier, we want to make sure that we have this desired property of not amplifying disturbances, even though the network might get new agents, change its structure, and so on. So there's been quite a bit of research already on large-scale interconnected systems. So you are surely familiar with the literature on stability, and also there's quite a lot on consensus synchronization. I could have the full screen here just with papers to the side. There are just a few here. And some then, there's also quite some work on performance of networks. So one of those performance measures is coherence. And basically it means if you zoom out from a formation and you look at it as a whole, you want to make sure that it stays coherent and it doesn't become too large by drawing apart. And that's something Bamier, for example, has been looking into quite a lot. And then there is this particular kind of network, which very often is, you can find in traffic networks, when you have strings, vehicle strings or vehicle platoons. And there is this effect called string stability or string instability, which has also drawn quite attention. And imagine you have a small perturbation acting on a vehicle that tries to follow a reference. And if you use a controller to follow that reference, despite the small perturbation or disturbance, the error will temporarily go up, but then the controller will make sure the error goes down to 0 again asymptotically, so everything is fine. Now, if this vehicle is followed by another vehicle that's trying to follow that one, for which we see the red curve, the next vehicle's motion will also be disturbed, so also the local controller will kick in, and so on, and it cascades through the string. And if you're unlucky, it looks like this. So this is string instability, and what you see here is that in the Lyapunov sense, this is still stable because the errors are bounded, and it's even asymptotically stable because the errors go to 0 after a while. The problem with string instability is that there does not exist a uniform bound on the errors. So the further down you are on the string, the bigger the maximum error will be. So that's something we don't want to have. What we want to have is string stability, and then the transient should look a bit like this. So yes, of course, this perturbation at the beginning of the string will trickle through the network, but the effect of it will be smaller and smaller and will not create trouble. So this is quite well known and well understood for strings, where the graph structure is a line, very simple. But what we've been interested in is looking into what happens now if I have a much more general network, an undirected network where agents talk to each other without having a prescribed structure. So our objectives then were to, first of all, define what is this notion. Because for string stability, one very useful definition is just that the local error of the next vehicle should be less or equal to the error of the preceding vehicle. If you have a specific order, like in a string, that makes total sense. In a network, there is no specific order, so it doesn't make sense. So we needed to, first of all, think about, okay, what kind of notion or definition would even be useful. Then look into, okay, can we ensure this is satisfied? Can we find conditions for it? And lately also we've been looking into, okay, how can we find appropriate distributed controller design mechanisms so that we set up the systems individually to make sure this condition, that whatever condition we find is satisfied. And scalable here, just to be clear, always means independent of the size of the network. So whatever we do, we don't want to restart the whole design just because a couple of agents join and we maxed out our n being the number of subsystems or agents in this. So we started, and when I say we here for the first part, this is Bart Besseling, who's now in Groningen, and me. We started looking into this. I think we were still both in Sweden, so a couple of years back. as a first step, we looked into a particular kind of large-scale networks where each subsystem sigma I has a state xi, of course, and its derivative is a nonlinear function of the state itself and some neighbors. And important here, those neighbors are relative neighbors. So relative neighbors in the sense that if you have a relative neighbor -1, then the relative neighbor of agent number 3 is agent 2. So you get some sort of ring structure. And you could also have a relative neighbor -1 and +1. So you get this bidirectional structure, and you can also include relative neighbor number 2 and so on. So you see there is a underlying structure that how you connect it to your neighbors doesn't change, and that creates some sort of ring structure here. That was important as a first step in order to derive conditions later. By the way, the red arrows here, these are the disturbances acting on each individual system. As you can see here, each differential equation also includes a disturbance here. And just to ease up our writing up the formulas, here's a shorthand or compact notation for the entire system altogether. And with this in hand, we then had a look at, okay, given we have such a system, what is a property that we would like to see? And we defined then scalable input to state stability as ISS, quite close to ISS, as you will see, because we say the system is SISS if there exists a KL function beta and a K infinity function sigma, such that the states of each individual agent is bounded by beta, depending on the initial condition on T. So that's the part that will die off with T. And the effect of the disturbances, and this being a K infinity function, the bigger the disturbance, the bigger the effect on the state deviations, of course. And as you can see here, what we are then expecting is that all the trajectories are in this sort of funnel here, where we have, you see the dashed part, which is the constant part due to the external disturbance, and then the part that's dying off from the initial conditions. Of course, as I said, this is inspired by ISS, and we used ISS because we wanted to look into nonlinear systems if possible. And by saying that this beta and the sigma should hold for any n, for any natural number n being the number of vehicles or subsystems in the system, it means that we are scalable because you can change the number of subsystems. You can just add agents and the same bound will still hold if that's satisfied. And if this still holds, then the norm or the effects, the accumulated effects of all the disturbances on every single agent will always be bounded. So it can never accumulate, it can never grow out of bound, as we saw with string stability. So that's basically what we want. Important here is we had to do a bit of a split. On the one hand, we created this definition, which is very general. So this definition, mind you, does not include any, say again. Okay. It does not include any assumptions about the system being homogeneous or spatially invariant. That was only for the condition we derived to show that the condition holds, or this property holds for some networks. So the definition of SISS is quite general to start with. Okay, but we wanted also not only to have a definition, but we looked into for which kind of systems we can prove that this holds. And that then brought us to this, at the beginning, very restrictive kind of system setting. And we assume that every subsystem is ISS. And if it is ISS, then there exists this positive, definite, readily unbounded function V. Anybody that has worked with ISS or Lyapunov functions will find the formulation somewhat familiar, I hope. So that is quite standard. This just says that every system itself is stable in that sense. But what we now add to it is to say, okay, if this is true and all the systems are ISS, if we also have a K infinity function rho such that this inequality here holds, then the overall system is SISS. And if you look a little bit deeper into it, you see, okay, this is the same function alpha that we have up here. It's the same for all the agents. And this then here sums over all in neighbors or relative neighbors. So you can see here, it's the same gamma j's. And rho has to be k infinity function. So that one here is then a negative part, which means it makes the left part of the equation, or this inequality rather, not equation, inequality, strictly less than 0. And that then allows us to show that the system will be SISS. There are relations to small gain theorem here. And if you're interested in the details, we can have a look later or have a look at the paper, just in case you're wondering. Yes, there is a connection. And what's particularly nice about it, what I like, is that it's a local condition. If this is satisfied for each agent, so if each agent has a function v that satisfies this condition here for this given alpha and gammas and a given rho, then by just making sure every agent follows or satisfies that condition, we can still ensure a global condition or a global performance measure on the entire network without having to know how big the network is or checking the entire network at once. And that's always what we want to do here. So we don't only want to be scalable in the sense that whatever we do can hold for any n, so any number of agents, but also we don't want to have conditions that need global knowledge or a global entity checking something, because that is not practical in reality. Okay, proof, very roughly, just 2 notes on that. We using the maximum overall agents here, and take the derivative to show then that the derivative is strictly negative, using the different, or has this strictly negative part here plus the effect of the disturbances. And if you have never seen this before, this is the Denis derivative. We use this, or we need this, because due to the maximum, the Vn is not always differentiable. Okay. So again, this is inspired by small gain theorem. And that's nice. You know, we got one step closer. we have a notion of better understanding what is actually what we want. Intuitively, we could do this by graphs or by curves. But we wanted to have it mathematical way, so we achieved this. We have some conditions on how to achieve this for some systems, but the interconnection structure is very, very limited. And we wanted to be able to show that something is scalable, or this network is scalable for any network. And we didn't, so we were wrestling a bit back and forth, and we decided, okay, maybe what we need to do is to look at the changes in the network. So what if you have a network and that changes over time? If we can make the changes itself scalable, so we can make the changes so that the overall performance measure doesn't change over time, we can be more flexible of what kind of structure we allow. Here we are only considering networks of a very rigid formation with these relative neighbors, so that whenever you add a new node, you know exactly how it's going to be connected, right? You don't have to worry about it. If you don't want that, you have to be more flexible what kind of structural changes or what kind of additional edges you allow if an agent joins. So that brings me to the next part of our work, where we also looked at large-scale interconnected systems, but because we realized we need to start slow, we backed off a bit on the system description part. And you see here a much simpler way of describing a node or an agent, where we went for linear dynamics with some AI here. And then the coupling are also linear. So MIJs are the coupling weights for the incoming neighbors. And XI, the states of the state of agent I, is even a scalar. Again, we can write this in compact notation. All the A's, these AIs here, we put in a big matrix A, which is diagonal matrix. And then these MIJs, we put into one big matrix M. So this then describes the entire network, and X is the vector of stacked states. And because now we are linear, we don't need SISS per se. We can get away with a much simpler one, which just combines or compares the norm of the disturbances going in and the norm of the maximum norm of the state deviations in the system. And we want this factor to be maximum gamma, because that allows us for a given size of a disturbance to estimate what is the worst case of states that we can expect. Okay, fair enough. So we got a much simpler system structure to start with in order to do some mathematical proofs and get a feeling how things work. And we got a notion of describing what we want to achieve. Now let's look at structural changes. Structural changes can be that can mean a lot of different things. So we decided to break that down into elementary structural changes, simple baby changes that then can be combined to describe much bigger changes. So those 4 elementary small changes are the following. First of all, you could add a node. So here, for example, on the right, we just add this node here in blue. And that means that your A matrix changes by getting another row and another column, and this self-feedback parameter AN+1 here. And your M matrix also grows in dimension by just adding zeros here. That's it. There's just an edge. There's just an additional node. It doesn't do anything else. You can also add edges. So in that case, your A matrix remains the same, and your M matrix changes one element according to whatever edge you're adding here. Okay, you can add some more edges here. You can also remove edges. You can see here that this edge here is about to be removed. Again, the A matrix remains the same, and in the M matrix, you change one element again by taking away the weight of that edge. And of course, you can remove some more edges if you like. And if you have a node that doesn't have any connections anymore, you can also remove that node, which means you take away this row and column relating to that node in A and also in M. And because there's no edges anymore connected to it, this row and column in M should be 0. Okay, so that's it. And a structural change then can always be described as a sequence of elementary structural changes. Fair enough. And then the idea was, if we make sure that each elementary structural change is scalable, and if we only allow structural changes that are a combination of elementary scalable changes, then we can change our network and maintain our property, our performance property. So what do we mean when a change is scalable? Well, if we change from system sigma to sigma bar, we say that this structural change is gamma scalable if both the system we started with and the one we are ending up with have this bound gamma. Okay, fine. And it's scalable. So this is for a given gamma. And gamma can be maybe very large if you're unlucky. But it's scalable if the lowest possible bound you can find on the system before the change is also the lowest possible bound on the system after the change. That's probably more what we intuitively think is scalable, but there's a slight difference here. Okay. As I said, if we make sure that all our changes are scalable or maybe gamma scalable, then we can preserve this performance measure. And this now allows us to consider very heterogeneous networks, because you can always create a network which is very heterogeneous by looking at the structural changes that you need to do in order to get to the network wherever you want to go to. Cool. Then luckily, we had chosen some simple system dynamics in order now to find some conditions under which this is true, or under which the changes are actually scalable. And we found out that the system, first of all, is gamma robust if and only if there is a vector V here. And all the inequalities in that part are element-wise. So V has to have positive entries, and then this inequality has to hold. And every entry in V has to be less or equal to gamma. And the smallest gamma for which these inequalities hold, you get from looking at a special version of this vector V, which is equal to, or we call U, which satisfies this inequality here with the identity. So this is gives you the smallest gain. So combining this means the system is gamma robust if and only if, first of all, the system is Hurwitz, right? I mean, that makes sense. If it's not stable in the traditional sense, we don't need to talk about scalability and robustness. And all elements of this U vector are smaller or equal to your upper bound gamma that you set. Cool. So with this now we can analyze this lemma and understand a bit better what does it mean and what does it tell us about the network and what kind of changes we can allow. So first of all, interestingly enough, you can look into this from a graph theoretic perspective by setting up a graph where the edges are your former former coupling weights MIJs or MJI divided by AI. And so you get this adjacency matrix equal to MA inverse. And then you can show that a walk from I to J, for example, from I here through those other nodes to J, has this accumulated weight. Okay, fair enough. And you can also show that the UJ times AJ minus 1 equals the sum of all weighted walks in this graph that end in J. Okay, fine. That's another technical result that you don't quite know yet why you need this for. You can also look at cycles. And if the system is gamma robust, then you can only have cycles where the weight satisfies this condition. Again, this goes, or it's related to small gain theorem. And now with all this in mind, let's have a look at the actual changes. And can we derive from there which elementary changes are scalable? Well, first of all, the removal of an edge and the removal of a node, both are trivial. So they're both scalable. Cool. The fun part is when you want to add something. That's when it's difficult or potentially more difficult. Adding a node is also scalable, even only if the self-feedback parameter of this new node is sufficiently large. That makes sense because if the node that you add is not connected to anything else in the network, you just have to make sure that the effects of the disturbances acting on that very node are not larger than your allowed gamma. So that's it. And the proofs there follow immediately by just looking at the dynamics. The most challenging part is adding an edge. And you can actually show that, let's say, if your system that you start with is gamma robust, then adding an edge is scalable from I to J, if and only if, of course, the new system is also Hurwitz. Adding an edge and destroying stability is not allowed, of course. And then this condition here is hold. And now we go back to these lemmas that I showed you earlier, and we can shed some light onto it. So this term down here is the sum of all walks from I to J. And this allows for the following interpretation. The denominator of that left-hand side here is related to the generation of cycles. So if you add a new edge here, does it generate a cycle from between I and J? And if so, then the cycle has to obey this condition I showed you earlier, that there are no cycles allowed that have that violate the small gain criterion. And the numerator actually is related to the additional propagation of the disturbances. So if there is a link now or an edge from J to I, that means that disturbances acting on J will also influence I and will influence any agent that is further down the path from I. So for example, K. And that allows us to derive the following corollary. If you have a system that's gamma robust and you have some node K where the kth entry in this U vector, remember the element-wise, all the U's have to be less or equal to gamma in order to be gamma robust, right? So if there is the element, the kth element belonging to the kth agent that is already maxed out, so to speak, this is equal to gamma, and you add any edge that to a node that also has a path somewhere to K, then the additional disturbance impact on that new node that gets an additional incoming edge will also propagate through somehow to node number k. And k is already maxed out. So you can interpret the element of u that belong to the kth agent to the local effect of the accumulated disturbances can have on that very agent. And that's already the maximum gamma. So by adding anything else, directly or indirectly to it, will mean this band will increase, means you cannot, you're not having the same gamma bound as before, means this is not scalable. Unless you do something else, maybe. Unfortunately, the first corollary here is difficult to check because you would need to know the different paths in the network, which is contradicting to what I said earlier. You want to have it locally. And one local way you can check is if your A minus M is strictly diagonal dominant, then you can check it only with scalable knowledge using this inequality. And if you have that, then this is conservative, of course, because you demand it to be strictly diagonal dominant, but at least then you have a decentralized verification of this centralized scalability property. Problem with that, it's analysis only. Nice to know if it's not scalable, but what do you want to do if you do want to have that additional edge? So what we need now is something constructive, something that allows us to adapt the system so that we can allow changes that without otherwise, according to this, would not be scalable. And how do we do this? Well, we now look into how would I need to adapt my self-feedback parameters AI locally in case, for example, I get an additional incoming edge that adds to this sum here. And in order for it to be interesting, we constrained our self-feedback parameters into this set curly A, simply because otherwise you just make AI larger every time and that's it. It's pretty boring. So we decided it's more realistic if you have constraints, because this is can be interpreted as an internal control, and very often we don't want our internal control to be very, very large because we have actuator constraints and cost energy, and it might have other negative impacts. So a very intuitive, simple problem to start with is to say, okay, we want to make sure we have some bound gamma star. So U has to be element-wise less than gamma star times the vector of ones. Okay, cool. And we want to achieve this with the minimum impact or with the minimum effort. And our effort is parameterized by AI. So we take the sum over all AI squared and minimize that. That's intuitive. And we can actually show that if U again is calculated by this equality that I showed you earlier, and you put all U's that are possible for all sorts of A in your constraint set into a set curly U. And if you assume that the optimal solution, or that the solution gamma star times vector of ones lies in this set, right? Then the optimal solution is equivalent to U being exactly equal to that vector. That makes intuitive sense, because if there would be one entry in U that's larger than gamma star, then gamma star is not the gamma you're looking for, but the norm is actually larger, so you can't allow that. And if there's one element in U that's smaller than gamma star, you could save energy, because that agent is putting in a little bit too much control effort by suppressing the disturbances more than it actually needed to meet that overall bound on gamma star. So you could actually reduce this control effort a tiny bit and increase that element of U to being equal to gamma star. So that makes sense. Very nice. Problem arises though if this solution is not in the set U. And then the whole problem becomes very ugly, non-convex. So we had to look for a remedy here. And one remedy was to formulate the problem differently. And the reason why, in order to come to a convex problem again, for which we know way better how to handle those with the existing theory. And you see here a optimization criterion that includes U transpose LU. And I think the second term is much easier to understand. The second term is the 2 norm of the difference between U and the vector of all gamma stars. Makes sense, because you want to achieve gamma stars, so you want to penalize the distance between what you have at the moment and the actual gamma star vector. The first one, the first term here makes sense if you now decompose this into local objective functions, because this translates into the square between the distances of ui, that's if you're agent I, and uj of your neighbors. So you compare your own entry in ui with the UJs of your neighbors. Why does that make sense? Well, because we know the optimal solution, if we want to spend the least amount of control effort into it, is that all the entries in U are the same. So if you have very different entries in U to your neighbors, more likely you're not close to the global optimum. So we penalize that part. And of course, you have these weighting factors here that can bring you closer to one or the other constraint. The algorithm is containing several large equations that are a little messy and contain a lot of notation. So I'm sparing you that, and I just give you what it does. So the first one is that you project onto your local constraint set. So in case in the last step of the algorithm, you got a AI that's just too large or too small for your local constraints on your self-feedback parameter. Then you take a step into the negative gradient direction. So classic strategy for optimization. And by doing this, you get your new value of UI, your own entry of U, the vector U, but also you get a new UJ for all your neighbors, and your neighbors get a new UJ for you. And then what you do is you communicate this to your neighbors, and you average over what your neighbors think about what your new UI should be. And this seems a little bit funny that you need this step, but look into the details later if you like. Only telling you for now that if you don't do this last step, you don't go necessarily in the direction of the global optimum, but you end up in a Nash equilibrium, so a local optimum. Okay, and a very last bit here. One big limitation that we had so far was looking into very, very simple networks or agents, where not only they were linear, but they were also scalar. So as a next step, we're looking at the moment into MIMO agents, where the states of each agent are a vector, and also the coupling between the agents are through the outputs that can be a vector as well. Apart from that, is the same general structure, and the theorem at the moment looks like this. So we can show that there exists, if we have some constant gamma dash, beta, and p, and also a matrix pi that is a norm greater or equal to this p that we set up here, and some parameter alpha I, that this here is a local parameter, all the other ones are the beta, gamma dash, and p are global for the entire network. And then if each individual agent has some local parameter alpha I and a matrix pi such that this big inequality holds, then the overall system is gamma robust, with gamma being the square root there. Why is that cool? Well, again, because that condition only contains information that agent I knows or can get easily from its direct neighbors. It contains the system matrices, the AI, the BIJs are between you and your direct neighbors, CJ, and so on. So how to find such a PI might be a difficult thing. We're working on that at the moment. And another thing we're working on at the moment, for some cases, you can show that such a PI cannot exist, meaning this agent will violate this condition, either because it has too many incoming agents or incoming edges from other people that are amplifying too much of their disturbance. It's all accumulating in this one, or because AI, this matrix here that basically includes the self-feedback control of agent I, is not enough to compensate that. And in that case, we have different options. Of course, we could get rid of some incoming connections, so reducing the sum here I mean, if you see that this should be, the left-hand side should be less or equal to 0, and this part here is clearly positive definite part, if you disregard or cut off some edges, then it might be easier. And another thing you can do is to adjust your own controller, so adjust your AI in order to force this inequality to hold again. So that's something we are looking at the moment. And another thing we're looking at, but it's too early to have slides on it, is going back to nonlinear systems. And hopefully one day we'll close the cycle. We're back to nonlinear systems, SISS, and more general networks, not the very restricted ones we started with. And that's it from me for now. Thank you very, very much. Thank you all for being here. Thank you online for listening. And also thanks to Bart Besseling and Magnus Axelsson Fisk, with whom I wrote those papers, and credit should also go to them, of course. Thank you. Venkat, do you want me to stop the recording, or do you want to have that running?
Yeah, if you not want the questions to be in the current video.
Yeah, I wonder if we can cut it off later if we want to. Sorry.
Do you think this is as far as you can get? Or do you think you can push these results further in some way?
I definitely think we can do more, because I think what we can do for sure is to better understand how we should adjust our controllers. At the moment, we have just a scalar controller that we're doing. It's very limited. That's something I want to do for sure. And for nonlinear systems, I think there is a lot open there. And then I also talked to Richard and Venkat today. So I see a lot of other connections where there's more interesting scenarios. For example, looking into what if you don't even know exactly your edge weights or your own dynamics, or what if you can't choose any controller, but you have to you're restricted to a certain class of controllers. So there are more things along the horizon that I can see.
So if you introduce an edge, if you introduce a node with an edge, and then that node has an disturbance coming into it, right?
Yeah.
If that, because of that addition, did you investigate the case like that disturbance because of the cycle comes back at you in a much bigger sense because of string instability?
Yeah, exactly. That's what is this condition where, you know, you remember this condition for adding an edge, and making sure that when you complete a cycle, that this cycle does not, if the disturbance running around one full cycle, that this is not amplified. This is included in this condition here. And that is, in a way, string stability, but with cycles in a network rather than just running along in one direction.
Because there might be multiple cycles and it will
amplify along. You're right. That makes it more complicated, but it's the same general idea behind it. You're right. And the cycles are particularly interesting because you must make sure that through a cycle it can even become unstable in the Lyapunov sense if you have something that amplifies. So then it's not only a performance problem because you have something that accumulates at some end of the graph and gets large annoyingly for some time, but it could even get worse and worse over time and become unstable.
Thank you. Yes. No, sorry.
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 So I didn't understand the intuition here why you wouldn't need the same result when you were removing an edge. I mean, because you could have cycles that would cancel out each other, right? Do you know what I mean?
I think that's something we looked into, and I think the crux is, let me go back to what you're saying makes total sense if this connection here would not be xj, but xj minus xi. So in consensus networks, very often you have here the relative influence. And then if you take away an edge, it does not only change the off-diagonal entry in your system dynamics, but also the one of the diagonal, because it also affects the factor in front of xi. So if you write in the consent, if you write your system structure in this typical consensus way, then actually removing and adding an edge can both be a problem. But by writing it this way, at least then removing edges is never a problem. But I think that you think it could have been is because you're more used to this other writing, other system description would be my guess.
But then it's also because MIJ is positive, right? If it can be negative.
Yeah, we didn't allow for negative ones.
Okay, so I think I missed the.
Yeah, I think
that
that is,
requirement.
yeah,
I think that's.
Or I have to check if we really did assume, oh yeah, the weights are positive here. Yeah, sorry.
Okay, even on slide. So,
Yeah. It's a good point. I mean, it's too much writing if one doesn't see it all. Sorry.
So you mentioned a number of applications in the beginning. Is there any particular application that has been inspiring this work?
For me, I started with string stability, so naturally I was drawn to robots driving or in a formation. And Magnus, my PhD student, he comes from electric engineering, so he's looking into power grids, and he thinks this is, at least for him, this is the main application. So in one of the papers, we also looked at DC grids in order to, as one of examples.
So the nonlinearities that you mentioned could be of interest. What type of nonlinearities would you get would be relevant for for those applications?
Yeah, for example, for power grids, I think sinusoids are quite relevant because you have the sine of the distance in the phase of agent I minus the phase of the related or agents that are connected to, and then it's not theta I minus theta j, but the sine of that. So then you've got sinusoids, and usually very often you simplify it by saying this, the differences are so small, so the sine is the same as the argument itself, but that could be one of them.
But for robotics, it would be quite different.
Yeah, for robotics, it could be stuff like dead zones, and depending on your gears and whatnot. I think that depends a lot on how much you go into the detail of the robot's motion itself. But it could also be that you have saturations, which are always a little ugly to handle, but it could be a natural constraint for a robot not to be able to go infinitely fast or accelerate very fast and so on.
Is it possible to extend this to systems which are actually still linear, but it's coupled with the dynamics of others, like
I guess it is.
Diagonal A matrix. Like,
I don't know.
instead of a diagonal A matrix,
Yeah.
you have like a non-diagonal A matrix. So it means that if node I's dynamics is affected by node J's dynamics.
I don't understand the question. So you mean that there's some part of the dynamics that is linear, but there are some that are nonlinear?
No, no.
Or that some agents are linear and some are
AIXI and AJXJ affects XI dot.
yeah.
So
that's what
It does through them. They
Yeah.
affect each other through them.
It could also be that you have just nonlinearities in a coupling or just nonlinearities in the internal dynamics. That's something up for debate in the next step. If I can do results for more general nonlinearities, fine. But I assume I will need some assumptions to start with. And which ones they are, I cannot tell yet. It's too early.
I was wondering about a specific on slide 7.
Seven, okay.
Yeah, where the scalable input state stability. So I was wondering if this condition, if it's conservative, or if you have any notion.
It most likely is, yeah. I mean,
Because it looks like almost too elegant to.
it is conservative because first of all, you need to have such a function here. And also it's conservative in the sense that it has to have the same function alpha for all agents. And it has to be the same functions gamma j for all agents. So all this is quite conservative. And I have some notes about how you can allow for some more heterogeneity here, but I did not write it up. So this one here is conservative because either the system is homogeneous to start with, which is already very conservative, or all the agents have to fit into this one condition where some agents, this function alpha here might be not feasible.
I have a question. You mentioned that there is a node that added to the network.
Yep.
And then next time you remove this node, so you add this node, remove this node, this kind of thing, does it cause some problems to the network?
So
The
you mean
frequency
there-
of adding an add or no, or removing an add or no?
You want to add a node or an edge?
Either or both.
Okay, okay. Well, you would do it, you would first, if you want to add something, you would first add the node and then add the edge. And adding the node is not a big issue. The condition is very little, very simple. Adding the edge depends a lot on where the edge is going to. Because if you add a new node, if you add a edge from a new node on an existing node, depending on how many incoming other edges this node has, this can be difficult. I wonder where I have this graph. Here. It depends a lot on the edge, but adding stuff is potentially creating trouble. That's why you need the conditions and check those. Removing edges or nodes is always scalable. So only adding is a difficulty. And then for the edge, it really depends on which direction and what the edge is connecting.
It doesn't matter how frequently I add or not, maybe I could add.
If you can show, I mean, yes, you will always have some transients by the time you add something because your disruptive system is like putting a step onto it. Ah, that's what you mean. So you mean if you keep on adding things while you're still in the transient to adapt to the new system structure. Oh, okay. That's something we haven't looked into. If you do it too frequent, like how does that, those transients due to the step response, so to speak, how does that accumulate? We haven't looked into this. It's a good question.
Actually, I think there are some people, Julian Hendricks and his group, they're looking into that in terms of, they call it open multi-agent systems.
Okay,
And they
cool.
look at nodes coming and going.
All right,
and
cool.
so-
That's, yeah, very
That's
relevant.
awesome.
Just haven't been able to
No,
come
I
around to
also
that yet.
haven't thought of that.
Okay, but that's, thanks for the comment. Very good. Richard, you had a question?
Yeah, so suppose I look at a very, very regular graph
Yeah.
structure, like an infinite lattice or something
Yeah.
like that. Would these conditions simplify so that I could quickly see if they hold or not? And then that would mean that network was stable, and also any network built by removing things from this regular lattice would also be stable. So you'd cover like an enormous family.
Yeah, I mean, you would have to look into, let me go to the condition for the edge. You would have to look into for your regular matrix, regular system, what exactly does that mean for your entries in A and M? And is it that regardless of the I and J that you choose, you have some regularity here? But that depends a lot on what kind of edge you want to add. I mean, the thing is that you,
I mean, start with something spatially invariant,
Mhm.
but very regular. Then maybe I can
Yeah, but-
diagonalize this with a
But what
Fourier transform or
do
something.
you have like a lattice and then you want to expand this by putting more things onto it?
I'm saying just analyze something huge with lots of edges and lots of nodes, and then because removing stuff doesn't break anything, then I know everything in between nothing.
Yeah.
And the extremely big regular thing will all be covered.
Yeah, if you have a very regular thing, I would look into if you can use this one here, this first result, because that is assuming that you have a very regular system structure. That's exactly the limitation of that one. But if that's not a limitation for you because all the agents are connected exactly in the same way, maybe something like this can help you. And then you know it is scalable, and then looking into removing things will not change that. So if you have something very regular to start with a bound that you're happy with, and then you start removing things, then you should be all right. So either or could work.
And could I see your monster formula at the end one more time?
That's not too bad. It does, you mean the LMI stuff?
Is it
Looks
an
like
LMI?
a.
This one?
Yeah, so I was gonna suggest that you multiply this on both sides by
Yeah.
PI inverse and then
Yes,
change all your.
I know it's
inverses
not an
into-
LMI yet, but it can be.
Yeah, I was just gonna say this, you can LMI this. If
Yeah.
you just put
I
everything
know
just-
this. I know this is not an LMI, but it's an inequality that you can solve with MATLAB I mean, it's a monster formula. I totally get you.
I'm just saying if you make your PIs inverses everywhere, then it will be an LMI.
But this is.
Yeah, but that's not my point.
This
I
is
know
convex in P, isn't it, already?
You've got products of PIs and
Yeah,
PJs.
Here, and here's even a PJ inverse. I know there's a bit of work to make this a proper LMI. It is possible. I just didn't want to have an even larger formula for you to
No,
enjoy.
No, but it'd be the same if you just multiply both sides by PI inverse and then call all your PI inverses QIs.
Yeah,
No,
that's
but
cool.
It's an element.
Richard, I don't think you need to do that, because every term there is convex in P.
Everyone wants to improve your.
But that was not even my point, but yeah, it's okay.
Every term is convex in P.
Take it as a challenge.
Feed it into CDX and we can do.
It'll just do it for you.
Yeah.
Okay.
Well, my point is here, it might look like a monster formula, but this is still solvable, and this is all local information. These are system matrices that you know, or you can even adapt potentially. You know your number of incoming agents. You know the coupling matrices, and okay, you need to know the output matrix of your neighbor. The neighbor has to tell you once. I think this is something that can be solved. And you need to know the biggest issue actually that you need to know the PJ of your neighbor, or you bound that because you know that P is also bound, PI for everyone is bounded by the scalar P here. So actually the biggest worry is this one, because it means agent I can check only if there is there exists a PI for this agent, if the agent knows what agent J is doing for all the neighbors. So that is more of an issue, but you can bound that, then becomes even more conservative, but at least you can solve it. Another option you can do is to say, well, scrap that. Agents don't get to have their own PI, but everybody uses the same matrix P. And then if agent I can't satisfy this, has to adapt its own feedback here or allow less incoming edges or something. But the main point of that inequality is that this is something that potentially every agent can check on its own to again have a condition that every agent checks locally to ensure a global performance measure, regardless of the size of the overall network. Even though, yes, this is not as nice and cozy as what we had before in terms of condition.
So if you keep on deleting edges, the graph can become disconnected?
Yeah.
Is that, do you care something about that, or?
If you
do
care
just
about
keep-
connectivity, yes, but if we only can care about how disturbances travel, then having disconnected parts is the best can happen, right? So, but yeah, you're right. Of course, there's a limit, and we have connected networks because we have some advantages of this connection.
Exactly, yeah.
You're completely right, but for this purpose here of keeping your gamma small, sure, remove all the edges, makes it very easy. So. Yeah, there are of course other reasons to have edges. They are not included. These reasons to have edges are not included here.
Okay. Is there any other thoughts or questions? Otherwise, I think we should thank the
Thank
speaker
you.
again and close this.
Thank you very much.
I made 2 copies from you.
Oh, wonderful.
This is Richard Murray's
Oh, yeah,
homepage,
yeah.
and here's a book you can download.
Okay, perfect. Thank you.
And this is the
Christian
Christian
Soltesz.
Soltesz. about
Perfect, so I
him,
can drop
so-
an email.
Yeah.
Thank you so much.
You're welcome. Thank you very much for coming. Very interesting stuff.
Thank
Yeah.
you. Cool. I'll keep those.
This is weird, yeah.
Scalable into the stake stability paper. I've read it like a number of times. And this
Which
is like
one?
The SISF paper.
Oh.
It was a while ago since I read it, but it was so good to finally get it presented.
I'm glad you enjoyed it. Okay. I can end.
Non-technical person.
Oh, wait, sorry, this is not my computer and I'm messing with, I'm so sorry, Venkat, I forgot.